Saying good morning to all. Good morning to all. Good morning to all. Am I audible? Okay, thank you. Welcome to the class Embedded Systems. Uh, in the previous class, we were discussing about the classification of embedded systems and the followed by the purpose of embedded systems and purpose of embedded system under which we understood the different purpose or why the embedded system is designed to serve the purpose of various tasks like data collection, storage, representation, or data communication, or data or signal processing, monitoring, control, and application specific user interface. In each of these purpose, we could undergo the different examples of real-time examples, and we understood the importance of the purpose of embedded system. Today, we'll start with a new topic. So let me present my screen here. Okay, I hope my screen is visible to all of you. Uh, so we done with the following topics as on today. That is embedded versus general purpose computing system, classification of embedded systems, major application and purpose of embedded systems. Today we will try to continue with the session on elements of embedded systems and differences between CISC and RISC architecture, Harvard and Princeton architectures. Okay, so coming to the typical embedded system. In a typical embedded system, if you observe this figure, so entire block diagram of embedded system can be observed here and different elements of that embedded system. In the beginning, so we understood that definition of embedded system. So wherein the definition of embedded system stands like it may be electronic system or electromagnetic system, right? So now again the embedded system main job is to for the computing, that is general purpose computing or specific requirement computing. So ultimately this system is also for used for computing purpose. Now when it is the but the embedded system is designed with a combination of special purpose hardware and the embedded OS, that is very important in order to execute a specific set of applications, right? Now if this is the embedded system, now if I consider the embedded system, that this embedded system consisting of different types of elements, maybe input ports or memory is one more important element, and communication interface is one more important element here, then output ports, then followed by any other peripheral integrated circuits. If I look this as an embedded system as a whole chip, the embedded system contains, so, see, this is the whole chip that you should consider. This is a system on chip and other peripherals here. Now, this system consisting of one of the hardcore system, and this hardcore system can be hardcore system can be a microprocessor or microcontroller or digital signal processor or application specific processor or sometimes even FPGA. So this is what the hardcore system we call it as. Then further, the embedded systems, hardware or software systems are basically designed to regulate input and output ports, which means that, see, when we design any of the embedded systems, the basic operation of embedded hardware or a software is to regulate a physical variables. When I say that variables, it is nothing but manipulating the inputs according to the expected outputs. It is regulate a physical variable or manipulate some of the devices by sending some control signal to the actuators. And these devices are connected to the output systems in response to input signal provided by the end users, like the sensors, where a sensor sends an input signal to a embedded system, where this embedded system consisting of the dedicated hardware followed by software, then it manipulates and it gives the control signal what job has to be performed, and this operation is performed by your actuators. Now apart from this, these input, what all these inputs? Apart from sensors, I also have input parts of interfacing devices like maybe the keyboard. I maybe the keyboard like one of the telephone systems, digital telephone system. We already gave an example. Like I press 1, 2, 3 as a keypad. So that digital keypad system of any telephone. So that could be the interfacing interfacing for this embedded system or any push button switches. Now again, when it comes to output interfacing devices, the interfacing devices for this may be a LED, right, or maybe a electronic buzzer or LCD displays or piezoelectric buzzers. These are the few output ports to be mentioned in the entire embedded system. So that's what we here we discussed, like the system core is nothing but your microprocessor or microcontroller or DSP ASIC based on the applications, and this input, this embedded system or hardware merely regulated or manipulated by the input and output ports, where these input and output ports consisting of a keyboard and LCD respectively as an input and output devices. Moving further, so this another important part of this element of this embedded system is memory. This is very important and responsible for holding the algorithm, because the system works either to read the input from the user or the input ports to perform based on the input read by the system. I need to activate or manipulate the output, then this has to send the signal to an actuator by reading signal from the input device. Now in order to perform this particular operation, there must be some instructions or a program or set of instructions. That's what we call it as a software that has to be resided in one of the memory system, right? So which is whole and sole responsible for a memory is to control that particular algorithm. And when I go to embedded systems, we have a different types of memory systems. Maybe it is a OTP. What do you mean by OTP here? One time programmable memory. See, I burn a program for only one time, that memory is freezed. If I want to use that reprogrammable, no, it is not possible. So that's where sometimes it's so happen, like often and often I need to change the program and I need to rewrite. In such cases, OTP kind of memories will not help me out. So what we do, we go for another type of memory called programmable read-only memories, wherein these kinds of read-only memories can be reprogrammed again and again. So that's what you did in your lab experiments in 8085 or lab, or even when HDL programming, when we try to flash the program for FPGA. First we will flash our Verilog code onto the PROM, then FPGA will read the data from memory, that is PROM. Okay, and even in your ARM programming, the same thing that has happened, right? This particular system core will always be reading from the memory called PROM. And another type of memory that most commonly used in an embedded system is ultraviolet electronically programmable read-only memory. PROM is again same, that is programmable read-only memory, but the burning of that particular PROM device, the way of burning, what we say, that is done through ultraviolet electronically programmable. And another one is EEPROM and flash memory. So probably you know that flash memory, you might have used this many times. The flash memory is nothing but your USB pen drive or SD cards. All are the examples for flash memory. So these are the different types. See, when we want to read a memory, see these SD cards kind of programming we will be using in Raspberry Pi. Raspberry Pi hardware will be having a SD card, and every time the Raspberry Pi will fetch the algorithm from the SD card itself. So these are all the different most common types of memories that we use in our embedded systems for controlling algorithm. Okay. Now moving further, little bit more about the memory. Uh, sometimes system requires a temporary memory, which means that the moment you turn off your system, the data is going to be erased. Temporary memory for performing some arithmetic or control algorithm execution, and this type of memory we call them as a working memory. Can you give me the example for working memory? Yeah, it is nothing but random access memory, RAM or RAM. Okay, so the RAM we usually call it as temporary memory or working memory. So that is random access memory is most commonly used a working memory. And apart from that RAM, we also have a dynamic RAM and non-volatile RAM that can be used as a the temporary memory for performing arithmetic operations, which means that whenever we try to execute any program, then all the program will be temporarily moved to RAM. And because in order to increase our execution speed, if you consider the any hardware, so here that is secondary memory, then followed by RAM, then followed by SRAM, then followed by processor. So this is processor, that is what CPU, that's what we call. Then this is SRAM. Okay, this is SRAM, and this is RAM, and this is secondary hardware. Secondary hardware may be your hard disk. Now the data will move from here to RAM. So once your system is started with BIOS operation, booted, then the part of a program that is required to run the system will come and sit in your RAM. then your program that is supposed to be executed will take some code memory in this. So this code memory will be executed at much faster rate. If the again piece of code must be executed again and again, say for example, now right now I'm using Google Meet again and again, then this part of memory will go and sit in my SRAM, because things that user is using the Google Meet again and again, and this part of piece of code will go and sit in my this particular SRAM. Because if that particular copy is already present in my SRAM, so it always fetches the processor. For processor, it is always easy to fetch from SRAM, so that the execution get much faster. That's what I gave an example in classroom while offline class was going on. So the kind of RAM that how we should treat is, so you have a books in your bag all the time. So the books which are very essentially required in every classrooms will be present in your notes, that will be present in your the copy of that will be present in your what's that your bag, and now your bag is something like your random access memory. So when it gives a very quick access. Now, if you feel that that particular book is not useful for another 1 week or one and a half week, then you keep that particular data in your rack, that in your home, right? So which is not frequently required. So what happens if I store it in my RAM or SRAM? So obviously that particular part of memory will going to kill unnecessary space, right? If you keep the unwanted books in your bag, it is consuming lot of memory there, right? Sometimes it so happen like which is actually required, you cannot keep it in your bag. So what you do, you remove unnecessary books that is not required for next one and a half week. You keep that aside. So this is how, in the same way, the algorithm is prepared to fetch the data from your hard disk to RAM and then RAM to processor. So ultimately, the execution of processor must be increased. The problem with this is RAM memory. The problem with this kind of memory is the data is kept only for a short time, and it has a short time memory. The reason is the moment you turn off the system, the entire data is going to be vanished. So that's what we call it as RAM is to be called as temporary memory. And there are some RAM which we also call them as non-volatile random access memory, where even until and unless you overwrite another program, the data will be present. So the kind of memory that LPC2148 is used is a NVRAM, because the moment you until and unless you reprogram it, even if I turn off the kit, and once again if I turn on the kit. So say for example, you have downloaded a stepper motor program, and once you're done with the lab, you switch off the system, and you also switch off the kit. Okay, now tomorrow when you come back to lab, so once again you on the same PC, if you turn on and if you turn on the kit, still the stepper motor program will be present, because the kind of RAM that we have used in that particular system is non-volatile. So once again, what happens, unless you reprogram, then you need to reprogram that particular code once again, then only the new program can able to execute. So if you want to execute tomorrow, if you want to execute DC motor program, then write a DC motor, run, put it on the RAM, and it particular program will go to execute. So that's how the NVRAM works. Now, the next topic is core of the embedded system. As I told you, this core of this embedded system, I'll just show you what is that. So this core, we are discussing about this particular core, system core. That is, the core of the embedded systems falls into one of the following categories, on which the central core is going to be built. So if you examine any of the embedded system in your real time, it is built on these one of the cores that is mentioned here. The core of the embedded system are of the following categories: general purpose and domain specific processor, application specific integrated circuits. In short, we call them as ASIC, ASIC ಅಂತನೂ ಕರಿತೀವಿ. And programmable logic devices, PLDs, and COTS, commercial off the shelf components. These are the systems or hardwares that we normally use. Okay, under general purpose or domain specific processors, we will be using the microprocessor here, or microcontrollers, or digital signal processors. The core embedded systems may be, once again, general purpose or application specific kind thing like FPGAs, or programmable logic devices, or it is COTS. Now we'll discuss one by one here about general purpose processors or domain specific processors. The digital signal processing is completely domain specific. Microcontroller may be a general purpose or sometimes domain specific. Even the same case is true with microprocessor, where sometimes we will be using that as a general purpose as well as micro domain specific. I'll just discuss about the difference between these two processors, that is microprocessors and microcontrollers. Then followed by, we'll move to what is digital signal processor and its applications. Many of the times I also talked about the differences between microprocessor and microcontroller. Once again, microcontroller is nothing but microprocessor plus the peripheral devices. This is the thumb rule that we must understand any of the time. That microcontroller must contain a processor. Without CPU, one cannot call it as a controller. The microcontroller must contain the CPU plus it will be containing some peripherals. We'll see the differences one by one here. A silicon chip representing the CPU, which is capable of performing arithmetic as well as logical operations according to the predefined instruction. That's what a simple CPU here. It is nothing but a chip which consisting of a ALU in simple. What about microcontroller? Microcontroller is a highly integrated chip which is containing CPU along with the CPU. Look at here, along with the CPU. Here it is only CPU plus the arithmetic logic unit, ALU. But here in this case, CPU plus random access memory plus special types of registers and on-chip memory, flash memory or read-only memory to store the program, and followed by timer and control units and dedicated input-output controllers. That's what here you can see, only CPU and ALU, and apart from the CPU, here the peripherals such as RAM, such as read-only memory, such as timer bar control unit, interrupt control units, and dedicated I/O ports. Combinedly, I call it as microcontrollers. Now, another difference between these two is it is a dependent. What do you mean by that? Because it requires a combinations of other chips. Now, here everything was built in on a system on chip. In a single chip, I used to have a timer, interrupt controller, flash memory, everything. But if I want to have this, so this is dependent, and hence it is dependent on the other chips like timer, program, data memory, and interrupt controller for its functioning. As and whenever the functions required, I need to integrate these two. So there was for 8085. 8085 was a simple processor, microprocessor. If I want to work with any timer operations or interrupt operations, I need to interface this chip 8085 chip with another interfacing circuit called 8255 IC. 8255 IC is another integrated circuit for timer operation. Okay, whereas in 8051 this timer is inbuilt on a single chip. So this is what we call it as a system on chip. The microcontroller 8085 the microcontroller 8051 contains timer circuit on the chip itself, but 8085 microprocessor does not contain any specific timers. If I want to use a timer IC, then again I should purchase one more IC called 8255 by the name called 8255. Then I should also know how to interface 8085 and 8255, because I will be writing the 8085 instructions in order to perform timer operation, right? Say for example, after 10 minutes I should turn on the buzzer, then it should count for 10 minutes, right? So which means that every time the signal instruction should move from 8085 to 8255 IC, then 8255 IC will be monitoring the count from 0000 to up to 111, which will be equivalent to 10 minutes. So this is how this interfacing knowledge, programming with respect to interfacing knowledge, I should have here. So that was the little tedious task with respect to microprocessors. Now another important difference is, most of the times we use these microprocessor for general purpose design, but here it is most oriented towards domain specific. Your Intel processor is a very good example for what is that, microprocessor. It's a processor, it's just a processor wherein the Intel processor is used for the general purpose, not any of the general domain specific. Coming to 8051, it is also a Intel processor, but it is not a, it is also from the Intel family, but we call it as a controller because I can use that controller for any domain specific approach. That domain specific, see, 8051 is present in your microwave oven. 8051 is present in your washing machine to control. It has a capacity to control the timing because it has inbuilt timer. But the same thing is not true. I cannot connect your laptop to your microwave oven to control the timing, right? Because it does not have a timer. If I want to have a timer, ಲ್ಯಾಪ್ಟಾಪಿಗೆ ಮತ್ತೊಂದು 8255 ಐ ಸಿ ತೊಗೊಂಡ್ಬಿಟ್ಟು ಮತ್ತೊಂದು ಇಂಟರ್ಫೇಸ್ ಮಾಡಬೇಕಾಗುತ್ತೆ. ಸೊ ದಿಸ್ ಇಸ್ ದ ಮೇಜರ್ ಡಿಫರೆನ್ಸ್ ಇನ್ ಮೈಕ್ರೋಪ್ರೊಸೆಸರ್ ಅಂಡ್ ಮೈಕ್ರೋಕಂಟ್ರೋಲರ್. And of course, which will be, it does not contain a built-in IO port, where in microprocessor do you find any IO ports here in your laptops? Is it possible, apart from the USB, is it possible to read any of the sensor kind of data? No, it is not possible. So if you want to read the sensor kind of data, then what is to be done? So you will shift from your laptop to some other application specific controllers, maybe Arduino or Raspberry Pi or any 8051 kind of controllers or RM controllers, right? So this is the difference. There is no built-in input output ports wherein functionality needs to be implemented with the help of if you want to implement, that's what you need to go for using 8255 IC, peripheral integrated circuit. But this is, whereas in case of this multiple built-in I/O ports are present in 8051. That's what microcontroller. So giving an example, you can write this as 805, 8085 as an example here. Here I can give 8051, okay, and 8086 is one more example here, 8086, followed by Intel. Both of them are from Intel once again, and Intel 4040. Intel 4040 is one more IC, and here you can take ARM controller, okay, and Cortex M3 controller, and even PIC, okay. This is one more microcontroller, okay. These are the different examples for microprocessor and microcontroller ICs. Then targeted for high-end market where performance is important. Targeted for embedded market where performance is not critical. At current demarcation is invalid. At present demarcation is invalid. Now earlier days, when see nowadays sometimes what happens, you cannot differentiate microcontroller and microprocessor because processor is so capable, it is as good as like a controller. That's what but very beginning to start with, the in earlier days this was the case. So target for high-end marketing system, and nowadays embedded system is more designed for more critical applications. That's what at the present it is not the kind of differentiation I cannot make at all. Limited power saving options compared to microcontrollers, includes lot of power saving modes. What do you mean by this? In a laptop, at the maximum you can make it to hibernate mode or sleep mode if you want to save your power settings. But in case of controller, I have various points where I can connect the power saving modes. If the processor is not reading any input signal, I can turn off those signals, because sometimes the controller is busy in displaying the output across the monitors. In such cases, I can also have control over my input ports so that I can save some power mode features, right? Take your example in case of the mobile phone itself. If you switch off internet, mobile data, hotspot, Wi-Fi, Bluetooth, all these are power saving modes itself. If you turn on all of them at a time, so you will lose your battery backup as early as possible. If you turn off all these, then yes, of course, there is a lot of features wherein you can have a power saving modes. Okay, so this is all about under general purpose processor, microprocessor and microcontrollers. Now we'll move to digital signal processors. What is digital signal processors? You already know it, which are more of something like 8-bit, 16-bit or 32-bit microprocessor itself. But these processors are special purpose, wherein these DSP processors are designed to meet computational demands, high-end mathematical computational demands and power constraints. So more often these are used like embedded audio video communication applications. A digital signal processor are 2 to 3 times much faster than your general purpose microprocessors, as they are used for signal processing applications. And of course, the architectural difference between these two is also different. We'll see what is that architectural difference in forthcoming classes. So coming to the typical what is that now, digital processor incorporates the following block sets. The following are the block sets that what the typical embedded digital signal processor includes. One is program memory. Why it is required? To store the algorithm or memory for storing the program required required to process the DSP signal processing data. That is program memory. What about data memory? So there are two different memories. Try to remember this. Memory itself divided into two parts. One to store program, another to store the data. Okay, that's what architectural difference I call them as. Working memory for storing temporary variables or a data. We use this data memory, and we also have a one computational engine which we usually call it as a arithmetic logic unit. And many this is not only one unit. Apart from the ALU application, specialized units called MAC multiply accumulator unit, MAC unit we call it as, and multiple hardware shifters. So these are the one of the unique feature compared to your microprocessor and microcontroller. In case of microcontroller, if you take an example like 8051, we don't had a dedicated MAC unit in 805, but this MAC unit is present in DSP processor. That's a major difference, because there the computation was more of logical computations. Here the computations comes with more of mathematical calculations in case of digital signal processor. Hence we have a specialized arithmetic units, MAC unit, and followed by the different specified shifters, because we need LSL and RSL. You know it. The moment I shift it left, it performs the multiplication. The moment I shift it right towards right, it performs the division operations. And apart from that, we also have a IO unit. So these are the four different typical DSP units. When in the importance of the IO unit to interface between the outside world and the DSP, where it is very responsible in capturing the signals to be processed. The best example is the image. I need to capture the image, then I need to process it and then display it. For this, in order to perform this, definitely I need a DSP processor itself. What are the applications? Maybe in audio video signal processing, telecommunication, multimedia applications. Apart from that, the digital signal processing employs the large amount of real-time calculations such as convolution, and of course sum of product is nothing but is a part of convolution algorithm itself. And fast Fourier transform, you already see how the complexity of the equation is involved, and it is discrete Fourier transform. We also have a discrete cosine DCT, short time wavelet transforms. All these are real time calculations and more of mathematical calculations. So these kinds of operations can be performed only by DSP, not by any other processors. So what are as I told you, 8085 is a best example for microprocessor. 8051 is the best example for controller. Then what about DSP processor? We have a processor called TMS from Texas Instruments. TMS 6516 Texas Instrument idu. So 6516 or 6006 are a different processors which are dedicated for digital signal processing. Okay. Now this is all about what we say typical embedded systems with general purpose and domain specific processors, where general purpose microprocessor and microcontroller, domain specific once again microcontroller and DSP processors. Now next, as I told you in one of the difference here, that is DSP processor, digital signal processor are of having much faster than the general purpose processors. because of architectural difference. Now, in the next topic, we'll move to what is this architectural difference, how these processors are built based on the different architectures. Okay. Our next topic is processor architectures. So, as we see in the figure, whenever I build any home, in order to build that particular home, it will be having its own architectures, right? Its own architecture. Similarly, whenever I want to construct processor, ಯಾವಾಗಾದ್ರೂ ನಾನು ಪ್ರೊಸೆಸರ್ನ ಬಿಲ್ಡ್ ಮಾಡಬೇಕು ಅಂತಂದ್ರೆ ಬೇಸ್ ಅಲ್ಲಿ ಒಂದು ಆರ್ಕಿಟೆಕ್ಚರ್ ಕೊಡಬೇಕಾಗುತ್ತೆ ನಾನು. ಸೊ ವಿಚ್ ಆರ್ ದ ಡಿಫರೆಂಟ್ ಟೈಪ್ಸ್ ಆಫ್ ಆರ್ಕಿಟೆಕ್ಚರ್ಸ್, ಪ್ರೊಸೆಸರ್ ಆರ್ಕಿಟೆಕ್ಚರ್ಸ್? These are the different types of processor architecture. The processor may be built on an architecture called RISC or CISC architecture. The processor is built based upon the Harvard or Von Neumann architecture. Von Neumann architecture is also called as Princeton architecture. The processor may be built on Big Indian or Little Indian. Sorry, spelling mistake. It is LITTLE. Little Endian processor architecture. Now we will discuss one by one what is RISC and CISC architecture and difference between CISC and RISC architecture. What are the difference between Von Neumann and Harvard architecture, and difference between Big Indian and Little. Apart from that, we also have one more type of architecture called load store architecture, which we always call it as a like part of pipelining architecture. Okay. Now, okay, coming to this CISC and RISC architecture. At the definition itself, you know that the RISC stands for Reduced Instruction Set Computer, and whereas for the CISC architecture, it is called as Complex Instruction Set Computer Architecture. Normally, the typical range in any of the RISC architecture you consider, normally reduced instruction set means number of instructions should be very less. Here it ranges from 30 to 40 instructions only. The processor or a controller which built on RISC platform, RISC architecture, will consisting of at the maximum of 30 to 40 instruction set. But number of instruction, if you observe in CISC based architecture, it is almost or I can call it as more than 255 instruction set. See, where is 255 and where is 30 to 40 instruction set? Sorry, 255 instruction set, which means you need to remember those many instruction set if you want to program in assembly level language. It's quite difficult job for us. In case of RISC architecture, very comfortably, if you it's only have a 30 to 40 instruction set, you can greater programming style you can make it out. So that's what very less number of instruction set, approximately 30 to 40, greater number of instruction set, which are almost 255 instruction set. Of course, CISC architecture don't have this feature called pipelining. What do you mean by pipelining? Whereas RISC architecture provides me a pipelining architecture which increases the speed of execution. What do you mean by pipelining architecture? See here, I'll just take on a blank slide here and I'll explain this, and I'll explain this pipelining, then we'll continue the differences in next class. Few more blank screen. Okay, now to make it white. Okay, now there is an instruction. For every instruction you consider, there are three operations. One is fetch, decode and execute. ಒಂದು ಇನ್ಸ್ಟ್ರಕ್ಷನ್ ಎಕ್ಸಿಕ್ಯೂಟ್ ಆಗಬೇಕಂತಂದ್ರೆ ತ್ರೀ ಪ್ರೋಸೆಸ್ ಆಗಬೇಕು ಮತ್ತೆ. ಸೇ ಫಾರ್ ಎಕ್ಸಾಂಪಲ್, ಐ ಹ್ಯಾವ್ ಮೂವ್ ಆರ್ ನಾಟ್, some immediate data, let me assume 20, and I have another data, move r1, another immediate data, say 50. Then another instruction, add r2 is my final destination, r0 and r1. Okay. Now if I want to perform this, if I want to execute this, processor will be performing three operations. One is fetch the instruction, decode it and execute it. First I need to fetch this instruction. I need to understand. See, move or not 20 and takshana process artha agodilla. It has to decode it because still it is in it is not at the level of binary. It is at the level of machine level language. Assembly level language is still at assembly level language. Still this assembly level language has to convert it into machine level language in the form of ones and zeros. That is what we call it as decode it. Decode it to its equivalent ASCII value and then decode it into its equivalent what's that equivalent binary value. Then that particular binary value is getting executed. Three process has to be followed in order to execute a single instruction. Okay, first instruction is execute ಆಯ್ತು. Second time it has to perform the same thing, fetch, decode, execute, fetch, decode, execute. Now look at this. If I consider the execution cycles irutte yavade ಒಂದು execution alli, right? Of first, second, third, fourth. Okay, so ಈ ತರ cycles irutte. Now in a first cycle, see that how many cycles? One cycle for fetch, one cycle for decode, one cycle for execute. Andre to execute this I required 3 cycles. I required another 3 cycles for this, another 3 cycles for this. Totally how many cycles that is required? 9 cycles. Maybe the cycles means the timing, maybe 1 minute or 2 minute or 3 minute, whatever. Totally 9 cycles it is required to execute this. Okay. Now is it not possible something like this? So one instruction no fetch adaga, one instruction fetch, decode, execute, idu sequential agutte. Eradane execution idu first cycle, second cycle, third cycle. E cycle odagade in the second cycle, is it not possible for me to fetch the instruction of a second instruction? It is not possible. Yes, it is always possible. This is first instruction, second move instruction, third is add instruction. During this I can go for fetch, decode and execute, which means that in a second instruction there are two operations is happening. One is decoding of first instruction, second one is fetching the second instruction. In third cycle, execution of first instruction and decoding the second instruction. Look at this. This is in the second. Now similarly on the third level, in the third stage, during this itself, fetch, decode and execute. See, in a third instruction it is not only doing the execution of first instruction, decoding of second instruction and fetching the third instruction. Is it not? Look at this. How many instruction now? How many cycles? 1, 2, 3, 4. In a fourth cycle, execution of second instruction and decoding of third instruction, and fifth, only 5 cycles if I go for including a pipelining. If I go for sequential execution, totally I am getting 9 cycles. If I go for pipeline execution, I can reduce it only in a 5 cycles. I can complete the job itself. But that is the importance of pipelining, and this is possible in RISC architecture. That's where we call it as 8051 don't have a pipelining, but ARM processor have a pipelined architecture. Pipelined architecture means this is what? Fetch, execute, decode, fetch, decode, execute. This is the fundamental stages for executing the instruction of any processor's instruction, and this can be done in the at the pipelining stage. So that's where we call it as in a RISC architecture, pipelining is allowed. Due to pipelining, the speed is going to be increased. Whereas in case of CISC architecture, this feature is not present. Okay, so let me stop my explanation here itself. We'll continue in next class. If you have any doubts, let me take up your doubts in next for the next 3 to 5 minutes. Okay. Any doubts, guys? Did you understood this pipelining concept? Or if you want me to explain, no issues. I'll explain it in once again in next class, and then I will move to the next further differences. Is that okay? Any doubts? Now tell me, which one is advantage? Whether RISC architecture is advantageous or CISC architecture is advantageous in execution speed? RISC is better or CISC is better? Okay. What about cost wise? Cost effective? RISC is cost effective or CISC is cost effective? Cost effective ಯಾವುದು cheap? CISC ಪ್ರೊಸೆಸರ್ ನ ಇದನ್ನ ಮಾಡಿದ್ರೆ ಚೀಪ್ ಆಗುತ್ತೋ ನನಗೆ, RISC ಆರ್ಕಿಟೆಕ್ಚರ್ ಗೆ ಹೋದ್ರೆ ಚೀಪ್ ಆಗಿ ಐಸಿ ನ ಕನ್ಸ್ಟ್ರಕ್ಟ್ ಮಾಡಬಹುದಾ? ಕಾಸ್ಟ್ ಎಫೆಕ್ಟಿವ್, ಕ್ವಿಕ್, ಎರಡರಲ್ಲಿ ಒಂದು ಯಾವುದೋ ಒಂದು ಆನ್ಸರ್ ಕೊಡ್ರಿ ನೋಡೋಣ ಅಂತ. ಆಮೇಲೆ risk is cost effective, right? You are telling that RISC is cost effective. Okay, we'll have the discussion on this tomorrow. Let me check whether you return with the same answer or you will flip with your answers. Okay guys, take care. Once again, see you, bye. Day after tomorrow, Tuesday at Wednesday we will see at 12 o'clock, or if there is is it okay if I engage at 8 to 9? Is it okay if I engage at 8 to 9? Let me know. Later on you can post it in WhatsApp group. Thank you.